Hi guys, we're going to talk about 7.7 acid rain. Now, all of you have taken chemistry, so you understand the impacts of acids and what they are. We're just going to kind of run through them real fast. Okay, so you've heard of the term pH before. It is a measure of the hydrogen ion concentration in water. Now, you may not remember this. Sometimes this is an AP information, but water can dissociate into an H plus ion and into an OH ion. And that H plus ion is what makes things acidic when you have that H plus ion. In 1 liter of water, we have 10 times 10 to the negative 7th moles of these H plus ions. Super tiny number. But we do have some of those H plus ions in water. Now this pH value is where we actually take the negative log of that H ion concentration. You don't need to do that, but you need to understand that the pH scale is a logarithmic scale. So it's based on levels of 10. So the negative log of 10 to the negative 7 for water equals 7. So pH of pure water is 7. You may have heard of different definitions for acids. We use different ones in AP Chem. But at the end of the day, an acid is something that when added to water causes the concentration of these hydrogen ions, these hydrogen plus ions, to increase. For example, if we add HCl, an acid, to water, it's going to break apart and we're going to get an H plus ion and a Cl minus ion. That Cl minus ion we don't care about, but that H plus ion, that is what's going to create that acidity. And by having now more of these H plus ions, we're going to take our concentration from 10 to the negative 7, which is what it was with water, to now 10 to the negative 2, which is going to take our pH from 7 to 2. So when we add more hydrogen ions, our pH number goes down. So let's just look at that math real fast. Before the acid, this was our molarity of our hydrogen ions. So it was 10 to the negative 7th, or a pH of 7. After it was added, this is our new molarity of hydrogen ions, a lot more. So now our pH is 2. I know you've seen this scale before. So this pH scale is how we rank acids and bases. We're not really going to focus on bases. When we get focused on other forms of pollution, bases can be an issue, but right now we're going to focus on acids. Acids are anything that is below 7. So going from 7, which is pure water, anything that's below. A lot of it our bodies can handle. Like we eat lemons, we eat grapes and tomatoes. However, it can be an issue for the environment. Okay, let's talk about just the purest rainwater. Because there is so much CO2 in our atmosphere actually produces acidic rainwater naturally. It forms carbonic acid. Water vapor and CO2 are going to mix together and they're going to form carbonic acid. Then this carbonic acid is going to dissociate into this water-forming hydrogen ion. So we have the carbonic acid, and then that H plus separates. And that H plus, as we remember, is what lowers the pH, making something more acidic. So our pure rainwater actually has a pH of around 5.6. So you need to keep that number in your brain. Regular rainwater automatically has a pH of 5.6. We tolerate this. Most of the environment tolerates that. For most things, that's in the tolerance range. However, that can change. This changes because of SO2 and NO2. SO2, as you remember, this is released by coal-fired power facilities, vehicles, combustion. we're going to create that SO2, and SO2 reacts with water to form sulfuric acid. Ooh, sulfuric acid's a nasty one. Same with our nitrogen oxide. Our nitrogen dioxide released from any combustion is going to react with water to form nitric acid. Ooh, so both of these, sulfuric acid, nitric acid, these are strong acids that have pH levels as low as 4. So all of a sudden, our water in the air is becoming acidic, and that creates something we call acid rain. Okay, so here we are, neutral water, right around 7. As we said, our normal rain is falling about 5.6. But ooh, this acidic rain is falling about 4.3 right here. Ugh. So you can see how it's becoming more acidic and could potentially be more influential on environments. And that's what we're going to look at. Okay, so the way that this acid rain can make an impact, it can happen in 2 different forms. It can happen in a wet variety or it can happen in a dry variety. We're going to take the term acid rain and we're going to change it into deposition, because we could have acidic snow, we could have acidic hail, we could have acidic rain, acidic sleet, whatever it is, but it is a form of deposition. So acidic deposition is our general term for the pH of this addition of SO2 and NO2 into the environment that is falling from the sky. It can happen in 2 ways. First is wet deposition. This is when rain, snow, fog, hail, whatever it is acidified by those compounds and then falls to the ground. Or we can have dry deposition. Dry deposition is when those particles, SO2, NO2, where they just happen to become solids and they fall on the ground and they're just kind of laying there. But then the water falls and all of a sudden now it combines and we have an acid. So the acid could form in the sky when it falls, or the acid could form when the solid mixes with the water on the ground. So here's an example of that. We have our man-made sources of our NOx's and our sulfur dioxides. They move up, they react with the water in the air. That cloud forms precipitation, and so we get wet deposition. Other times, we just have these pollutants, these particles in the air, and then they just happen to fall to the ground. And that would create dry deposition. Now, the last thing I want to remind you is that we do have natural sources of NO2, and that would be volcanoes. Volcanoes can release nitrogen dioxide into the environment. So it's not all man-made sources, but most of it is. Okay, so now let's look at how this has an impact. So this acid deposition, whether it's wet or dry, is generally found what we call downwind of locations where we have a lot of coal being burned or a lot of electricity plants. And the key area for this in the United States right now, this is important if you're looking at schools, is in this area right here, kind of West Virginia, Ohio, a little bit of Kentucky area. There's a lot of coal power plants right here. So they're releasing all these NO2s, all these SO2s in the air. And if you remember, our ferrule cells are blowing the winds in this direction. Our trade winds are blowing from the west to the east. And so that is why the acid rain is actually falling all up in this area, because the wind is blowing in this direction. It picks up the pollutants in this area and then deposits them in the New England, New York, Pennsylvania, Washington, D.C. area. So let's talk about what the impacts are of this acid rain. We've seen both human impacts and we've also seen environmental impacts. The first thing, the whole reason where we're like, something's going on is because there were a lot of carbonate structures. Carbonate meaning marble or limestone. So these gorgeous sculptures that are being built. And people love creating things out of marble or limestone because it's soft. But those things are made out of carbonate, and acid loves reacting with carbonate. This acid rain would rain down and cause a lot of damage to these buildings, these roads, these bridges, these sculptures, and these very cultural treasures because of how low that pH is and how that acid is reacting with that carbonate ion. This is another example. This is part of the Acropolis in Greece. And a lot of people go to these and they're like, wow, the detail of these women is absolutely like exquisite. And then they realize, any of you studying art history, the real ones were actually moved indoors. And that is because of the acid rain. This is built out of limestone, and the acid rain has caused destructive effects on these beautiful women. And they've said, nope, we're going to make copies, because otherwise the acid rain is going to completely destroy how these women look and this incredible cultural piece that so many people value. This is another one. Some of these treasures are just too large to move. And a lot of times in these big sandstone pieces, the carbonates are kind of what keep the rock together. And those carbonates are being dissolved. So here's another example. So much acid rain over time has dissolved this structure's body. It also corrodes metal and weakens bridges. That's another issue. So metals will react with acids. And so over time, bridges, structures, ships have actually seen a lot of corrosion, a lot of damage due to this acid rain. So now let's look at how freshwater organisms are being affected by these pH changes that happen due to the acid rain. So if you remind yourselves, neutral is right around 6. We're going to call that 6. That's like a healthy lake area is 6. But as we get lower, all the way to 4, all fish are dying at 4.2. Eggs, tadpoles, crayfish, other animals are dying at 5.5. If you're a fish, you are breathing in oxygen through your gills, and as that pH drops, it's actually like you're breathing like with sandpaper. So every time you open up your gills, it's like sandpaper. It's a horrible experience for them. So that acid is having a massive effect on their ability to survive. Okay. So rainwater is acidic. It drops down into the soil. But lucky for us, the earth has come up with this buffer system. And this buffer system is these minerals in the soil, especially limestone, that actually neutralizes that acid. These are things like carbonates, sulfates, aluminum silicates. They're all in the soil. So as that rainwater trickles in, they take the pH from a 4 and then they bump it up to a 6 by the time it reaches the lakes and the streams. So this is a fantastic ability that our natural systems have developed to kind of deal with this acid rain that is happening. That means that some areas, like this is in China here, are much less affected by acid deposition because they have so much calcium carbonate everywhere. And that calcium carbonate is reacting with the acids, reducing the acidity that is going into the waters. This is a beautiful part of southeastern China, and these are all limestone rocks. Now, unfortunately, in Korea, we don't have limestone rocks. We have a lot more granite. And so therefore, we have a lot more issues with acid rain than they do down in this part of China. Now, unfortunately, over time, the buffering minerals in the soil, they can become depleted. Every time a hydrogen comes in and reacts with a carbonate, that carbonate is gone. It's moving into the water with that hydrogen. So we eventually will run out of those things. So we'll see lakes where the pH is neutral, 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 neutral. Then all of a sudden it will spike and it will just drop. Because all of a sudden that means our soil has become depleted and it can't buffer anymore. And that will kill a lot of organisms. This process will also increase the aluminum levels because every time those carbonates or those silicates are being buffered and they're following the hydrogen into the water, those bits are breaking away from aluminum, meaning aluminum is now available to move into the waters or move into the oceans or the lakes or the streams. And aluminum can have a large impact on aquatic organisms. Just talking about how when this acidic water reacts, these aluminum ions all of a sudden become available and they can now start moving. It's almost like they become released and they become very harmful to organisms. The last thing I want to talk about is the damage that can happen to trees. So when we have this acidic deposition hitting newly formed leaves, and newly formed leaves are happening at the top of the trees, they can't handle this low pH. And so very often they are going to die. So it's going to stunt the growth of the trees in that area. So we can tell if we have acid deposition damage because you've got these just weird, we call this crown dieback, where the top of the tree doesn't have a lot of leaves. We just have this trunk sticking out. Also, we find that some of the nitrogen-fixing bacteria in the soil also die off. And so our soil becomes less fertile. So unfortunately, sometimes acid rain can create destruction of large forests, and it looks like this, especially up in the New England area in the US. It can also kill a lot of fish. We've talked about that as well. All right, so real fast, last minute things on how we can reduce acid rain. Burn less fossil fuel. Use less LPG. That is like, it is LPG, it's a better, cleaner version of fuel. It burns a lot cleaner than gasoline or diesel does. As I mentioned before, diesel has a lot of sulfur in it. We can burn higher quality and low sulfur coal. So we want to make sure we're getting that gorgeous black coal and not burning the brown coal. If we have to, that means we're going to wash the coal before we use it to remove that sulfur. Employ some scrubbing technologies, which we're going to talk about a little bit later. And then switch to electrical vehicles. We've talked about this before, how even those, they still require power plants, but at least they're not combusting. All right, I can't wait to experiment with you guys. Have a good night.